Okay, thank you very much. It's a pleasure to see everyone. And I was saying earlier, since I'm looking out of my window at a gray sky and snow, perhaps I wish I was in Chile right now rather than in Chicago, but I'll carry on. So the title of the talk is The Gravitino Swampland. And this is a preliminary results and work I'm doing with a former postdoc of mine in Chicago, Andrew Long, who's now an assistant professor at Rice University, and Evan, who's currently a postdoc of mine at Kavli Institute for Cosmological Physics. So any mistakes or problems or errors are all my fault, and not, of course, the fault of the junior people. All right, so I'm going to talk about gravitational particle production in the early universe. And there are various ways you can imagine gravitational particle production. And one way is just, let me see if I can get my pointer here, is just the exchange of a graviton with standard model plasma particles, scattering, annihilating, and producing particles through just gravity by exchange of a graviton. Another way you might imagine gravitational particle production in the early universe is if there are primordial black holes and they evaporate. And another way gravitational particle productions may be relevant in the early universe is displacing some scalar field from the minimum of its potential due to quantum fluctuations, say during inflation. And then as the field then oscillates around the minimum of the potential, you can imagine this as particle creation. This is sort of the picture for axion production. But the gravitational particle production I will concentrate on has to do with the non-adiabatic evolution of the mode functions during and after inflation. So the idea is that you start in an adiabatic vacuum during inflation, and in the far distant past, in the far distant future, you're in Minkowski space, approximately an adiabatic vacuum, and in the evolution, then there's mode mixing and you produce particles. And this is something that's well known. It was first pointed out by Schrödinger in 1939. So the idea is the expansion of the universe creates particles if the Lagrangian involving that field breaks Weyl conformal symmetry. And there's a critical expansion rate, which is equal to the mass of the particle. And the rate of creation of the particles due to the expansion of the universe is e to the minus pi times the critical value of h, or m, divided by h. And this is an analogy with the Schwinger effect, the creation of the instability of the QED vacuum. And Schwinger was a person who really did the final calculation of this in 1951, but there were people who talked about it earlier, Salter, Heisenberg, and Euler, and Weisskopf. And the idea is that the QED vacuum is unstable. There's a critical electric field, the mass squared, or about 10 to the 16 volts per centimeter. Not an electric field that's easily made in your basement. And the decay rate of the vacuum is e to the minus pi times E critical over E. So I'm going to explore gravitational particle production, in particular with spin 3/2 particles during the inflationary epoch through its gravitational interaction. And I'm going to assume I have in quotes standard quantum field theory, although I will talk about supergravity because I'm talking about spin 3/2 particles, and I'm going to assume standard general relativity. And this is part of a program that I've been involved with for 20 years now, calculating the 1, 2, and 3 point functions for all different types of fields. The 1 point function gives us the number density, the 2 point function, the isocurvature, and the 3-point function describes non-Gaussianities that are produced. So there's a program of calculating 1-point, 2-point, and 3-point functions, and the observables here are dark matter, isocurvature fluctuations, and CMB non-Gaussianities. And just marching down, studying massive conformally coupled scalar field, massive minimally coupled scalar field, massive Dirac field, spin 1 massive field to Proca-de Broglie field. And what I'll talk about today is the massive Rarita-Schwinger field for spin 3 halves. And I'm also involved in a collaboration with Rachel Rosen in progress, looking at massive spin 2, massive Ferrix-Pauling. So this is the aspect I will talk about today. All right, so spin 3 halves is familiar to some people, maybe not to everyone. It was first really put on the footing of quantum field theory by Rarita and Schwinger in 1941. And the spin 3 halves field, denoted as psi sub mu, is a vector spinner. And from the representations of the Lorentz group, it arises from the direct product of a vector and a spinner, and describes a spin 3 halves, at least some components of this decomposition, describe a spin 3 half field with helicities plus and minus a half, and plus or minus 3 halves. Some of you are quite familiar with the idea that quantum field theory for spins greater than 1 is quite tricky. Some people might think quantum field theory for any spin is tricky, but in particular for spin larger than 1, especially if you leave Minkowski space, there's a possibility of acausal propagation, gauche, wrong numbers of degrees of freedom. And for those of us who have played around with spin 3 halves and spin 1 fields in gravity are quite familiar with this. For spin 3 halves fields, many of the issues, quantum field theory issues, are resolved in the context of supergravity, where the spin 3 halves field is known as the gravitino, and it's the super partner of the graviton. It's in a multiplet with the graviton, and it receives its mass from the super Higgs mechanism. There is a Goldstino field, which is the fermionic field in the Cairo multiplet that provides the extra degree of freedom to give the spin 3 halves field its mass. And it can be quite complicated in general supergravity. You have to worry about torsion. There are 2 and 4 fermion interactions, and all these, well, many of the complications will be ignored in this presentation because I don't think they're relevant. In some supergravity models, the gravitino mass is time dependent in FRW models, and this will become important. So first, in this presentation, I'm going to just study straight ahead Rarita-Schwinger field in FRW, but allowing the mass to vanish. And here I have some useful references that will be in the record. So I'm going to start with the Rarita-Schwinger action in FRW. There's many messy technical steps. And you can project in terms of mode functions 2 propagating degrees of freedom with polarizations 3 halves and 1 half. And the field equations for the Fourier modes in conformal time eta, the helicity 3 halves mode looks like a regular Dirac equation for a spin 1 half fermion, but the spin 3 half, the spin 1 half component does not look like a Dirac fermion because there are these terms that enter the field equation. So looking at this, the dispersion relation for a spin 3 halves field will be CA squared plus CB squared plus A squared M squared. Now, CA and CB turns out to be complicated functions in FRW of the expansion rate, the Ricci scalar, the mass, and also the evolution of the mass, the change of the mass with conformal time, if that's part of the theory. And square root of CA squared plus CB squared plays the role of the sound speed. So this is the sound speed, and it's written here in FRW in terms of the expansion rate, the Ricci scalar, the evolution of the mass with respect to conformal time, and the mass of the field. And this can be expressed in FRW in terms of the energy density and the pressure in the following form. So first, let's take the case where the mass is constant. And you see that the sound speed vanishes if the pressure is 3m squared times the Planck mass squared. Now, this can easily happen after inflation because the inflaton field after inflation has damped oscillations about the minimum of the potential, and this leads to damped oscillations in the pressure and energy density. This is a graph of the pressure normalized by the expansion rate at the end of inflation and the Planck mass as a function of the scale factor after inflation. And you can see the oscillations in the pressure. So if you just look at this being zero, ignore this term for a moment, you will see that the sound speed will vanish when 3m squared divided by he squared is less than 0.5. Or the mass over the expansion rate at the end of inflation is less than 0.41. So this is a graph of the sound speed squared for various values of the mass over the expansion rate at the end of inflation. If the mass is small compared to the expansion rate at the end of inflation, then after inflation, the sound speed vanishes many times in the evolution of the universe. If this ratio is larger than 0.4, here illustrated with 1, then the sound speed does not vanish, but it can drop significantly below 1. And as this mass increases, notice the different scale here, eventually the sound speed will just approach 1 at all times. So this evolution of the sound speed, and in particular the vanishing of the sound speed, let's see, that was a point I wanted to make, didn't make it here, but if the sound speed vanishes, then if you look at the dispersion relation, there is no cost in the gravitational production of modes with arbitrarily high momentum. There is a runaway. And that's illustrated here by calculating the mode density defined in such a way that the number density is given by an integral over the number density. And this is the case if this ratio of the mass to the expansion rate at the end of inflation is 0.01. So you see that there's a runaway, an arbitrarily large, this is for the helicity 1/2 mode, which depends upon the sound speed. And for arbitrarily high K, you can produce the modes because there's no cost in doing it. The helicity 3/2 mode has a sound speed always equal to 1. And this is exactly what you would get for a Dirac fermion for gravitational production. This is the result if the mass is larger than 1. It's not a runaway, but it can be significantly enhanced over the value of the helicity 3/2, which is the Dirac fermion. Okay, so that's ignoring just straight ahead massive Rarita-Schwinger. Now, the interest in spin 3/2 field has to do with supergravity, and let's just look at n=1 supergravity in 4 dimensions. And you have to determine the number of chiral superfields, the superpotential, and the Kähler potential. In general, for n=1, d=4 supergravity, the mass is going to change in the evolution of the universe, and the energy density and the pressure is going to depend upon the gravitino mass. And there are many models on the market. The first model that people studied for gravitational production was in 1999. This is Giudice et al. And Renata Kalosh et al. And they just did a simple model of a simple Kähler potential, a simple superpotential. And when they calculated R squared, they found a seemingly miraculous cancellation to give R squared always equal to 1. So the term that's proportional to the change in the mass with respect to time exactly cancels this term, and it ends up being 1. So there's no runaway particle production if you have a supergravity with one Cairo superfield and this Kähler potential in this superpotential. Now, that was 20th century supergravity model building. Now there are many, generally people consider many superfields, nilpotent, superpotent, omnipotent, whatever. And the gravitino can either be massless, constant mass in various implementations, and whether there's a runaway or not depends on the number of superfields and the mass of the gravitino divided by the expansion rate. So in the paper, we discussed the criteria to have the sound speed always equal to 1. And in terms of the superpotential and the various Cairo fields in the potential, this sum, this is the result. And the reason, so to have R squared equal to 1, you must have the square of the sum equal to the sum of the squares. How can you have that? If you only have one term. If you have more than one term, more than one Cairo superfield, then you will not guarantee not to satisfy this, and R squared will not be 1. So in order to avoid runaway particle production, you have to have the sum of this, you have to have one Cairo superfield or the gravitino mass larger than the expansion rate at the end of inflation.
Rocky, I'm sorry, the chairman has to point out, this is a little bit like the Gong Show. You have 15 minutes for your talk and 5 minutes for discussion.
Okay, this is my last slide.
Good.
We assume that consistent theories of quantum gravity should be non-pathological in all gravitational backgrounds, and that gravitational particle production of arbitrarily high k-modes is a pathology. And theories that do not satisfy these two requirements live in the swampland. And we demonstrated that four-dimensional theories with light spin 3/2 particles, like the gravitino, generically exhibit this pathology, are not a low energy limit of quantum gravity, and therefore reside in the swampland. And I'll just close by saying swamps can be beautiful. I'm from Louisiana. I guess you must have swamps in Chile. You have everything in Chile. So the swamps are beautiful. However, in Louisiana, at least, most of the life in the swamp will sting, bite, or eat you. So let's be careful about the swampland. Thank you.
Thank you. Let's see if there are any questions.
I have a question.
Yes.
Yeah, this discussion you make is very similar to field theory at finite temperature somehow. There you have some kind of phase transition when, for instance, the mass as a function of temperature will vanish or something like this. There is a cross relation.
Yeah, there is a connection. So I think of what's happening is just particle production in an external field. And the external field is provided by the gravitational field. So if you have a time varying gravitational field, you can mix the positive and energy frequency modes of any field that you have. Thanks for the question, Jorge.
If the chairman can be allowed a question also, a quick one. Maybe I misunderstood something fundamental, but I would have thought that this really is a pathology if they have this explosion of the high modes. I mean, it doesn't sound physical. Do you agree with that?
Yeah, I don't know how to interpret it. It looks, we call it pathological. It's there in the equation. So we assume it's a pathology. And there's other examples of higher spin quantum field theories in gravitational particle production. For instance, for massive spin 2 particles, there's something known as the Higuchi bound. And if the mass is smaller than h, then you have ghosts. So generally higher spins greater than 1 field theories in gravitational backgrounds are really tricky.
Okay, right. I mean, inconsistent, you would say maybe. Would you say inconsistent?
I'm sorry?
Would you say inconsistent? There's something wrong.
Yeah, there's something wrong. Exactly.
Okay. Yeah. Okay. Thank you.